Continuous tracking of vital signs can be instrumental for eliciting healthy behaviors and early diagnosis of diseases. For example, increase in resting heart rate is associated with cardiovascular disease, and the scale of resting respiration rate is associated with acute stroke. Although current wearable technologies such as wristbands and chest vests can monitor vital signs, they are uncomfortable for continuous use and unsuitable for people with skin allergy and dementia. Radio frequency signals, as an alternative medium, can overcome such limitations and enable contactless vital sign sensing. In the past few decades, radar has been extensively explored as an RF sensor for vital signs. The basic principle is that the rhythmical heartbeat and respiration-induced chest movement reflects and modulates the RF signals, which can be detected by radar using phase, frequency, or Doppler feature extraction. Correspondingly, different hardware and signal processing schemes have been investigated to enhance the sensing range and accuracy. Most of the existing vital sign sensing systems work under controlled settings, where the human subject stays still in front of the radar. Several recent systems investigated restricted mobility scenarios, where the subjects may perform in-place typing, fidgeting activities, or move the body regularly back and forth. However, in practical scenarios, the subject may engage in a much wider scale of body activities, such as walking, household chores, fitness exercise, and random limb stretching. Such ambulant activities may intensively distort the radar signal pattern, immersing the vital sign-induced features, thus inhibiting the parameter estimation. To our knowledge, RF-based vital sign sensing under ambulant daily living conditions remains an open challenge today. In this paper, we propose a general model to remove the motion artifacts and enable RF vital sign sensing in ambulant conditions. Our model builds on insights from physiological and medical research, which indicate that human vital signs can be affected by body movement in a predictable way. We thus use a radar sensor to detect vital signs along with motion intensity. Specifically, we opportunistically call on the radar sensor, using it to obtain a baseline heart rate and respiration rate estimation only when the subject is static. Otherwise, whenever movement is detected, we predict the heart rate and respiration rate on the top of the baseline, rather than dealing with motion contact RF signals directly. To incorporate these design principles into a unified framework, we design a deep learning framework which can extrapolate both heart rate and respiration rate despite the motion artifacts. Now we demonstrate our solution under different kinds of movement. The first one is periodical movement. The object is jogging in front of the radar. The distance between them is about 1.5 meters. In the meanwhile, the radar is transmitting signal towards the object and receives the reflection. We first extract the movement power from the reflections using the proposed movement detection module. The movement power reflects the intensity and the frequency of the movement. Each peak of the curve corresponds to a maximum speed of the movement during jogging, such as waving arms. Then we estimate heart rate and respiration rate using our customized LSTM modules respectively. These modules accept movement power as input and output real-time heart rate and respiration rate correspondingly. We showed an example of real-time heart rate estimation curve and corresponding ground truth collected by professional equipment. We can find that the estimation is very close to the ground truth, indicating that the effectiveness of our model. Now we test another kind of movement, random movement. The object is doing some arbitrary motion, such as turning around and raising arms. We can observe the movement power that is show a completely different patterns to previous movement, which does not contain regular peaks. Although the movement pattern has changed, the LSTM could still learn the correlation between movement power and vital signs and show low estimation error. This shows the generalization applicability of our solution under different kinds of movement. Now let's demonstrate existing methods on the same test environment, which use frequency analysis to extract vital signs. This is the phase variation curve under periodical movement, and the corresponding frequency spectrum. We can observe fierce interference on the phase variation, which distorts the regular vibration of respiration and heartbeats. Also, from the frequency spectrum, we cannot observe sharp peaks in the spectrum like in static. It indicates that the traditional methods fail at extracting valid information.